Okay, I'm Javier Minguez. Thanks a lot for the invitation to the Fundación. And I'm going to talk about, or I'm trying to give you the view of a new trend that is coming in medicine. It's called digital neurotherapeutics. And I'm going to try to use a very plain language in the shape that you understand better what is coming instead of going to deep details. So digital therapeutics, it's about overcoming time, place, and patient constraints in order to have early access to the healthcare. And these are software-driven technologies, where the hardware, say, EEG brain monitoring technologies or brain stimulation, is just a peripheric. The most important core of the technology is the hardware, so the software and the artificial intelligence. So we recognize from day one that there would be a lot of innovation in the hardware space, but one after the other, they will be diluted, and the most important will be the software and the artificial intelligence. So today, I'm going to give you four views of how this field is evolving. So the first thing that we need to develop is hardware that is able to penetrate in our lives. So this is the objective. So we need to create medical-grade EEG brain monitoring devices that can be used anytime, everywhere, and almost by everybody. So there are many different ways to do it. Our bet was smart textiles because, one, we think that garments are a very acceptable instrument for society, and they have very high usability and ergonomy. And second, when you lie the development of a sensor technology into the textile industry, first, you reduce the costs because you don't have metal, plastics, and so on. And second, you can very easily remanufacture the device to be acceptable by elder people, young people, and so on. So let me give you an example. Can we have the video running, please? So this is, can we? I don't know.
Hi, my name is Adrian, and I have 12 years old. I'm going to show you how I put my neuro headband.
This is a child with 12 years old. He's going to use a technology that in the next 1 year and a half or something will be a medical-grade device. And just to give you the idea and the feeling how these technologies are evolving today, and we think that very soon it will reach society.
The ears between the ear flaps.
The kid is saying the ears between the ear flaps. For those that understand EEG, they are putting the ground and the reference in the ears.
Now I'm going to wait to the green lights.
Well, the green lights are the impedance checking, so the technology is checking whether the quality of the signal is correct and informing the user with red lights or green lights. Okay? So you will see in the screen. Red lights, checking, and green lights is ready. For those that understand EEG, the kid just close the eyes, and you can see very nice alpha waves in the EEG. And this is the idea. So these are the technologies that we think they will start to penetrate the society. Okay?
And
that's all. Cool. So the next ingredient that we have is the artificial intelligence. So let's jump to a completely different space. This is sleep medicine. And in the sleep medicine, today, at least in Aragon, you need to wait like 6 to 8 months to have a sleep study due to the space constraints, the number of beds in the hospitals, and second, professional constraints. It takes 2 hours to analyze visually the result of the sleep study. So there are a lot of researchers, MIT, Israel, here in Spain, and so on, that we are building artificial intelligence technology to automatically decode the full data. Okay? And today, many groups are able to achieve more than 80% of accuracy only using a few sensors in the frontal area. This is very relevant because the medical standard is 80% of accuracy. So there will be a lot of technologies that will be solving this clinical space very, very, very soon. Okay? But what is relevant for me today is how we are going to use this artificial intelligence to build a therapy later on. And let's jump to the next scenario, okay, which is cognitive enhancement that we can use for healthy, but also for treatment. Here, I'm going to use an example that we are developing that is neuromodulation, auditory stimulation during sleep for cognitive enhancement. We are applying this for mild cognitive impairment treatment, which is the preclinical stage of dementia and Alzheimer, okay? But there are many groups developing this. Can we have the video running, please? Well, the setup, it's aligned to what I mentioned before. So we have a person sleeping with the band. We have a small surface in the table, and we have a couple of low-cost speakers in the bed. So the band is reading the EEG. In real time, the artificial intelligence is decoding, and you can see here the 3 stages: wake, light, and deep sleep. And the idea is that we need to create a slow oscillation in deep sleep. Why? Because, can we stop the video, please, for 1 second? Sorry. Why? Because first, memory consolidation mainly happens during sleep. Second, because the more slow oscillations at the magnitude that we have, the greater episodic memory that we have when we wake up. And third, with a very well-calibrated auditory stimulation during sleep, we can artificially create more magnitude and slow oscillation. The question is how we do it, and here's the machine. So we are reading, now can we go forward? The artificial intelligence is in light sleep, okay? And what you are gonna see here is the signal processing technique. On top is the real EEG, the bottom that we create. Now we are in deep sleep, the technique starts to look for the slow wave, and this is the estimation, what you see. It says, I want to create this slow oscillation here, and we are gonna do with 3 auditory tones that are not gonna wake the patient. It takes a while. Clack, clack, clack. And you can see on top the slow oscillation, the slow oscillation, the slow oscillation. We are going to do it again. Clack, clack, clack. 1 is correct, the second is correct, the third is a little bit misaligned yet. So still, we are handling these problems of inter and intra-subject variability. But what you can see here is that a technology with artificial intelligence identifying in real time deep sleep, trying to create these slow waves and performing this in real life. So there is a lot of evidence today that validates that these technologies are increasing declarative memory right now, and there are a lot of groups trying to use this in mild cognitive impairment, Parkinson, and so on. And I'm going to go through another example, which is in awake. So it's neuromodulation by neurofeedback. So there is a very specific biomarkers in humans that is called individual alpha desynchronization that we can measure in task-related EEG. In short, the greater this biomarker, the more cognitive capabilities measured in terms of working memory and sustained attention. The difficulty is that this biomarker has a tremendous inter and intra-subject variability, and of course, we are going to try to modify, so also intra-sensation variability. The question is, how do you modify it? So the way that we do it is, can we go through the video? The way that we do it is similar. We have the patient with the band in real time is measuring the EEG. We have the patient very well calibrated, so we know what's the biomarkers from the person in the moment of use of the technology, and then we create a very simple neurofeedback process. We tell the patient, you need to put this square in red color, and then what you see is that we are going to give positive feedback to the patient. In the center of this line, when it's increasing, you see red, and when it's down, it's blue. At the end of the day, the person tries to learn how to put this square in red. What is happening is that he can learn if and only if he is producing the change in the brain in the way that we want. In this case, increasing the magnitude of this biomarker. So this intervention is a much larger evidence state in health is in meta-analysis, and there are different groups now adapting to the different pathologies. In our case, we are right now under clinical trial with mild cognitive impairment. And just to finish, I want to open several 3 topics for discussion. The first one is, well, of course, with these wearables, we are using low-density EEG. We take the advantage of having artificial intelligence in the equation to handle this, but are we going to be able to put all these therapies in the house of the people? The answer is not. We are not going to be able. It will depend a lot on the relation between the technology, the artificial intelligence, and the therapy. In my opinion, one of the most evolved domains right now is sleep, because we see that the artificial intelligence is really able to maneuver with a small number of sensors. The second important thing is researchers and regulatory bodies, we will have to understand the position of these new technologies with respect to others in the house of the people. And I'm telling this because you might have mentioned that or see that we are using auditory stimulation and visual stimulation, which are very, say, mild ways to stimulate the brain. There are others that we see here, we're going to see electrical, magnetical, and so on. Okay? So, of course, this technology may have more efficacy, but we lose in efficacy, and we get lower risk. So we'll have to maneuver and make the balance together. And finally, I think that these therapies are opening a tremendous new dimension of adoption. And it's why? Because it enables us to perform very large clinical trials with a very long time periods. And one of the good examples here is that think for 1 second, if we have to do a clinical trials with 300 people using this technology every day in a year, is around 100,000 sessions, which is very difficult to implement in the real life. So these new digital therapeutics are opening the doors for this clinical trial and adoption of these technologies. Thanks a lot for your attention.
Wow.